When we describe a AC circuit with a voltage source and some impedance in a box with a voltage and a current, that we saw that when we write V equals ZI, and we write the impedance as an amplitude and a modulus and a phase, then what we said was that if we know Z, that we can put in V naught e to the I omega t equals Z times e to the I delta times I naught e to the I omega t e to the minus I phi. In order for this equation to work, we can divide through by the time dependence, and we see that the modulus is equal to V naught over I naught, and the phase, delta, is phi. Now, we reversed what we did because now what we want to do is we want to use this to calculate the impedance for a variety of specific examples: a resistor, a capacitor, and an inductor. And we'll be able to write our Z if we can solve for the modulus and the phase. So now let's set up the first simple example, which is just a pure resistor, R with a voltage and a current. The physics that comes in is that V equals Ri. So right away, because R is a real number, these quantities will have the same phase, and so we expect that the phase to be 0 and the amplitudes to be related by V naught over I is just the resistance. But let's take a look at that. So we put in our V naught e to the I omega t equals R times I naught e to the I omega t e to the minus I phi. And we're doing this approach because when we get to a capacitor and an inductor, it's a little more complicated. So we'll see it in this very simple case. We divide out by e to the I omega t, and we get that V naught equals R I naught e to the minus I phi. Now, the only way that you can have a real quantity equal to, this has to be real, but e to the minus I phi is a complex number. What we have to do is set phi. This shows us that phi must be 0 in order to have real equal to real. And our ratio, R, is equal to V naught over I naught. So when we compare what we had over here, we see that R is the modulus of the impedance, and this is equal to the phase. So this is kind of a curious process. Here we define how to go from Z to phi and I naught, and now we're just reverting it, and we're getting phi and I naught and figuring out with Z what the impedance is based on our physical principle of voltage equals resistance times current for the single element. And so we see that the impedance is a pure real number, R.